Hello there. I never know how to greet you people, but today I'm talking about the Frechet derivative. So here we go. So in this lecture, I'm assuming that you have some background. In particular, I'm assuming that you've had a few calculus courses covering single variable, multivariable, and vector valued functions. And I'm assuming that you've covered the concepts of limit and continuity and derivative for these types of functions. I will briefly be mentioning an integral in one example problem, but it's not critical, so if you've forgotten what an integral is, you can probably get by. I'm also assuming that you've had a linear algebra course covering the concepts of vector space and basis, as well as linear transformation and matrix, in particular, the matrix representation of a linear transformation with respect to bases of vector spaces. So we recall that in calculus, the derivative of a function at a point, when it exists, provides a good linear approximation to the function values near the point. So to illustrate this, we've drawn here the graph of a function f, and a point x0, y0 on this graph. And in orange, we've drawn the line tangent to f at x0, y0. And the equation of this line is just y minus y0 is equal to f prime at x0 times the quantity x minus x0. Of course, f prime at x0 is just the derivative of f at x0. So this derivative gives the slope of the tangent line. And for values of x near x0, the change in f, in other words, f of x minus y0, is approximately equal to the derivative f prime at x0 times the quantity x minus x0. So this is the linear approximation for a real valued function of a single real variable. In calculus, of course, we compute derivatives of functions f from Euclidean space Rn to Rm. And there's several special cases here. So when n is equal to 1 and m is equal to 1, that's just the simple case of a real valued function of a single real variable, and derivatives are just numbers as we saw above. When n is equal to 1 and m is greater than 1, we're dealing with vector-valued functions of a single real variable, and the derivatives are just vectors. When n is greater than 1 and m is equal to 1, we are dealing with real-valued functions of multiple real variables, and the derivatives are just gradient vectors. And finally, when n is greater than 1 and m is greater than 1, we're dealing with vector-valued functions of multiple real variables, and the derivatives are just Jacobian matrices. So again, I'm assuming that you've seen these notions of derivative in calculus. The Frechet derivative, which is what we're studying in this lecture, subsumes and significantly generalizes these notions of derivative from calculus using the concept of linear operator. So this notion of derivative was developed by Maurice Frechet, and in order to present the definition of the Frechet derivative, we first need to define some preliminary concepts. So let's start with the definition of a norm. Let V be a vector space over R. Again, I'm assuming you're familiar with the concept of a vector space. Intuitively, a norm provides a means to measure the length or the magnitude or the size of a vector in a vector space. Formally, we say that a norm on V is just a function from V to R satisfying the following four properties or axioms. The first is positivity. The norm of V is greater than or equal to 0 for all V and V. The next is definiteness. The norm of V is equal to 0 if and only if V is the 0 vector. The third is homogeneity. The norm of T times V is equal to the absolute value of T times the norm of V for all scalars T in R and vectors V in V. And finally, the triangle inequality. The norm of V plus W is less than or equal to the norm of V plus the norm of W for all V and W in V. Intuitively, if we're thinking of the norm as the length of a vector, then these properties are very natural. The length is always non-negative, and it's 0 if and only if we're dealing with the 0 vector. If we have a vector V and we scale it by a scalar t, then the length changes by the absolute value of t. Finally, the triangle inequality is best viewed in R2, or the Euclidean plane. If I have a vector v and a vector w, and I compute the vector sum using the parallelogram rule, You can see clearly here that the length of v plus w is always going to be less than or equal to the length of v plus the length of w. In other words, the length of a side of a triangle is always less than or equal to the sum of the lengths of the other two sides. Now that we have the notion of a norm, we can define a normed linear space. A normed linear space is just a pair V norm, where V is a vector space and norm is a norm on V. In what follows, we're going to use V and W to denote normed linear spaces. In other words, we're not going to explicitly write out the pair. We're also going to use the double bar notation to denote a norm, regardless of which normed linear space we're talking about. The context will always make clear which norm is intended. So let's look at a few examples of normed linear spaces. The first is a simple one, the real numbers under the absolute value function. So we know that the reals form a vector space, and you can easily verify that the absolute value function satisfies the properties of a norm. More generally, Euclidean space Rn under the Euclidean norm, where the norm of a tuple x1 to xn is just the square root of the sum of the squares of the components, also forms a normed linear space. For a slightly more complicated example, consider the space CAB of continuous real-valued functions f on a closed bounded interval AB. This forms a vector space because we can add and scalar multiply these functions pointwise, and it forms a normed linear space under what's called the sup norm, where the norm of f is defined to be the supremum, or least upper bound, of the absolute values of f of t, where t ranges over all of the inputs in the interval AB. By the extreme value theorem from calculus, this is equivalent to taking the maximum of the absolute values of f of t, where t ranges over the interval AB. So here what we're doing is we're measuring the size or magnitude of such a function by considering the maximum size or magnitude of its values. Note that this space is very different than a Euclidean space because it's actually infinite dimensional. Similarly, we can consider the space CKAB of k-time continuously differentiable functions under the sup norm. So here, a function in CKAB has k continuous derivatives. Now, we've been talking about normed linear spaces. A normed linear space is a special type of metric space because the norm induces a metric or distance function in the following way. We define the distance between two vectors v and w to be the norm of the difference v minus w, and intuitively this represents the distance between the two vectors v and w. This distance function satisfies a number of natural properties which can actually be axiomatized to develop the general notion of a metric space, but we're not going to do that here. The metric allows us to define topological notions like limit and continuity in a normed linear space. So here's how we can define limit. Let Vn be a sequence in V and let little v be a fixed vector in V. Then the limit as n goes to infinity of Vn is equal to V by definition if the limit as n goes to infinity of the norm of Vn minus V is equal to 0. Recall that the norm of Vn minus V is the distance between Vn and V. So intuitively what we're saying is that the vectors Vn converge to V if the distances between them go to 0 as n goes to infinity. At first glance, this looks a little circular, but it's really not, because we're defining the notion of convergence in the normed linear space V in terms of the notion of convergence in the real numbers R, which we already know about. With this definition of limit, we can easily define the notion of continuity. So let f be a function from V to W. Then f is continuous at V and V by definition if whenever Vn is a sequence in V and the limit of Vn is equal to V, then the limit of f of Vn is equal to f of V. Note that the first limit is happening in V, whereas the second limit is happening in W. Under these definitions, many, but not all, familiar properties from Euclidean space Rn hold. We're not going to develop the general theory of continuous functions, but we will just use whatever we need. An important special case is the continuity of linear transformations. So a linear transformation T from V to W is continuous if and only if it's bounded, in the sense that the set of norms of vectors Tx, where x is a vector with norm less than or equal to 1, is bounded. It takes a moment to digest that, but geometrically what it means is that T maps the closed unit ball in V, in other words the set of vectors in V with norm less than or equal to 1, into some closed ball of finite radius about the origin in W. So now that we understand continuity for linear transformations, we're going to define a linear operator to be a continuous linear transformation. Note that this definition is not universal. Some authors use the term linear operator for what we've called a linear transformation, but for our purposes it's convenient to always require continuity for a linear operator. Given a linear operator T from V to W, we can define its norm by the supremum of the set of norms of vectors Tx, where x is a vector with norm less than or equal to 1. Recall that in the proposition we just proved, we learned that for a linear operator, this set is bounded, so the supremum or least upper bound is well defined and is finite. So essentially what we're doing here is we're measuring the size or magnitude of the operator T by measuring the maximum of the size of a vector in the image of the closed unit ball under T. That's not quite right because supremum is not the same as maximum, but it's good enough for a geometrical picture. Now, if we consider the set LVW of linear operators between V and W, that forms a vector space because we can add and scalar multiply these operators pointwise. It forms a normed linear space under the operator norm defined here. So finally, we can present the definition of the Frechet derivative. Let f be a function from V to W. Then f is Frechet differentiable at the vector v in V if there exists a linear operator T from V to W which well approximates the change in f at V, in the sense that this limit is 0. I'll discuss this limit more in a minute. The operator T, which can be shown to be unique, is called the differential or derivative of f at V, and is denoted by df at V. It's important to be careful with the notation here. Note that df at V is not a vector in W, but a linear operator from V to W. So df at V itself takes in vectors in V and returns vectors in W. So let's look at this limit more closely. The limit just says that the differential of f at V well approximates the change in f at V relative to the change in V. We can see this by looking at the quantity in the limit. The quantity is a ratio between numerator and denominator. Because it goes to 0, this means the numerator must go to 0. So let's first focus on that. The quantity h represents a change in V. So the quantity f of V plus h minus f of V represents the change in f at V when V is changed by h. The quantity f of V plus h minus f of V minus t of h therefore represents the difference between that change in f at V and the value of the differential evaluated at h. The norm of that difference, of course, represents the distance between those two quantities. So the fact that this numerator goes to 0 means that the differential of f at V provides better and better approximations to the change of f at V as h, the change in V, goes to 0. But what about the norm of h occurring in the denominator? The fact that the ratio goes to 0 means that the numerator must go to 0 faster than the denominator. In other words, the differential of f at V provides approximations that are good relative to the change in V. So even if the change in V is really, really small, the approximation in the change of f at V provided by the differential is still good relative to that very small change in V. So what does this definition amount to for real-valued functions of a single real variable? Well, in this case, it's just ordinary differentiability, and the differential of f at x at h is just f prime at x times h. It's instructive to see how we can prove that. So for t, a linear operator on R, and values x and h in R with h not equal to 0, the quantity occurring in the limit in the definition of the Frechet derivative just reduces to the absolute value of the difference quotient, f of x plus h minus f of x over h, minus t of 1. So if f is Frechet differentiable at x, we can let t be df at x and let h go to 0. Since the left-hand side of the equality goes to 0, that means that the right-hand side goes to 0, which means that the limit of the difference quotient, f of x plus h minus f of x over h, is just t of 1. But the limit of that difference quotient by definition is just the ordinary derivative of f at x. So we get that df at x at 1 is just f prime of x. By linearity, that means that df at x at h is just f prime of x times h. Conversely, if f prime of x exists, we can just let t of h be f prime at x times h. We can then show, using the above equality in the reverse direction, that t satisfies all of the properties required of the Frechet derivative of f at x. So what we're seeing in this case is actually an instance of a general phenomenon. Recall from linear algebra that a linear transformation is uniquely determined by its action on a basis. That means if v1 to vn is a basis for v, and v is a vector in v, then there exists scalars alpha I in R unique such that v is the sum, or linear combination, alpha 1 v1 plus through alpha n vn. If t from v to w is linear, then t of v is just a linear combination alpha 1 tv1 plus through alpha n tvn. So the vectors tv1 to tvn determine the behavior of t, and represent t with respect to this basis. So for the case we're considering of a function f from R to R, df at x is linear on R, and the number 1 is the standard basis for R. So the number df at x at 1, which we know to be f prime at x, uniquely represents df at x with respect to this basis. In calculus, of course, the derivative of f at x is just defined to be the number f prime at x, instead of the linear transformation df at x. But not everybody is super happy about this. The mathematician Dieudonné calls this subservience to the shibboleth of numerical interpretation, feeling it obscures the fundamental idea of linear approximation, especially in higher dimensions. Speaking of higher dimensions, what about the case of a function f from R to Rm, where m is greater than 1, in other words, a vector-valued function of a single real variable? Let's let f1 to fm represent the component functions of f. In this case, you can show, using an argument similar to the one I gave above, that df at x at 1 is just the vector whose components are f1 prime at x to fm prime at x, which is usually denoted f prime at x. So again, we have that the differential of f at x at h is just f prime at x times h. Here, df at x is uniquely represented by the vector quantity f prime at x, which again is usually taken as the definition of the derivative of f at x in calculus. What about the case f from Rn to R with n greater than 1? In other words, the case of a real-valued function of multiple real variables. This case is a little more complicated. For h in Rn with norm of h equal to 1, in other words, a unit vector h in Euclidean space Rn, the differential value df at x at h is just the directional derivative, which is given by the limit as t goes to 0 of the difference quotient f of x plus th minus f of x over t. In particular, if ei is the ith standard basis vector for Rn, then df at x at ei is just the ith partial derivative of f. In other words, df at x at ei is just the partial of f with respect to the ith variable xi, evaluated at x. Here, df at x is uniquely represented by the gradient vector, del f at x, whose components are the partials of f with respect to the variables x1 to xn, evaluated at x. The gradient of f at x uniquely represents the differential of f at x in the sense that df at x at h is just the gradient of f at x dotted with h, where the dot is just the vector dot product. In calculus, the derivative of f at x is defined to be the gradient of f at x. Finally, what about a function f from Rn to Rm, where both n and m are greater than 1? In this case, df at x, like any linear transformation from Rn to Rm, is uniquely represented by its m by n matrix with respect to the standard bases in Rn and Rm. In this case, the ijth entry of the matrix is the partial of the component function fi with respect to the variable xj, evaluated at x. This is called the Jacobian matrix of f at x, and is taken as the definition of the derivative of f at x in calculus. So we see that the Frechet derivative includes all the familiar derivatives from calculus as special cases. But it's also far more general. So to illustrate this, let's look at a simple problem from the calculus of variations. This is the problem of minimizing the arc length of a curve between 2 points. So given 2 points, AY and BZ, find a curve with minimal arc length between these 2 points. So recall that for a function phi, which is continuously differentiable on the interval AB, that the arc length of its graph is given by an integral L of phi, which is defined to be the integral from A to B of the square root of 1 plus phi prime squared, where phi prime is the derivative of phi. We want to find such a phi with phi of A equal to y and phi of B equal to z, which minimizes this function L. Now intuitively we know that this should be a straight line, but how can we prove this? So in calculus, we look for a minimum of a differentiable function f from R to R at its critical points x, where f prime at x is equal to 0. With the Frechet derivative, we can apply the same idea here and look at phi with dl at phi equal to 0. This is true even though L is an integral operator defined on the infinite dimensional space C1AB, where our critical points, so to speak, are functions. When we do this, we find that phi prime must be constant, so phi must be a straight line between the points as expected. Now obviously this is a very simple problem because we had an intuitively obvious answer, but this same idea can be used to solve much more complicated problems. For example, with the Brochristochrone problem, you're trying to find a curve between 2 points A and B that minimizes the amount of time needed for a point mass with zero friction to move along the curve between the 2 points. In this problem, the amount of time needed for the point mass to move between the 2 points A and B is given by an integral operator, and the solution can be found by minimizing the integral operator in a way similar to what we saw above. For more information, I suggest looking at this problem on Wikipedia. The Frechet derivative satisfies many familiar properties from calculus. As one example, let's take a look at the chain rule. So let u, v, and w be normed linear spaces. Let f be a function from u to v, g be a function from v to w, and h be the composite function g after f which maps from u to w. If f is differentiable at v in v, and g is differentiable at f of v, then h is differentiable at v, and the differential of h at v is just the composite of the differential of g at f of v and the differential of f at v. It's important to emphasize that this is just composition of linear operators. What this says is that in order to approximate the change in h at v, we can first approximate the change in f at v, and then approximate the change in g at f of v. This is very natural and straightforward in terms of linear operators. Now, in the case of real-valued functions of single real variables, this yields the familiar rule that h prime at x is just g prime at f of x times f prime at x. This just states a multiplicative relationship between numbers. At another extreme, if u is equal to Rn and v is equal to Rm and w is equal to Rk, then this yields a disgusting rule, which I'm not even going to read, stating a relationship between the partial derivatives of h and the partial derivatives of g and f. As Dieudonné states, here we have lost any trace of intuitive meaning. We see that it is much simpler to view the chain rule from the perspective of linear operators. So in conclusion, we've seen that the Frechet derivative subsumes the familiar derivatives from calculus, generalizes the derivative to normed linear spaces, satisfies many of the familiar properties from calculus, and leads to elegant and powerful results, for example in the calculus of variations. I encourage you to read more about the Frechet derivative. I highly recommend Dupree and Schwartz's book Introduction to Real Analysis and Dieudonné's book Foundations of Modern Analysis. You can also find lots of information on Wikipedia and on Google. Thanks for watching.